I'll say a few words. Welcome. This is our first meeting back this fall for the Gauge Theory Virtual Seminar. We are pleased to have Sherry Gong with us, speaking about non-orientable link cobordisms and torsion order and floor homology. Next week, we'll have Dong Hao Wang speaking about about monopole floor homology for three manifolds with toroidal boundary. I put a link so that you can find all of the talks. Comment that Sherry's preferred way for people to ask questions is just to unmute and ask, though I will monitor the chat in case somebody puts something there. And with that, I'll turn off my video to give us more bandwidth and let Sherry take it away.
Okay. All right. Thanks for coming, everyone. And thank you so much for the introduction, Dave, and for inviting me. Okay. So today I'm going to be talking about non-orientable link cobordisms and torsion in floor homologies. So what we're going to be doing is we're going to be studying smoothly embedded, smoothly embedded, not necessarily oriented cobordisms, pretty much primarily between knots. Okay, so there have been a few recent studies about the non-orientable cobordism, the genus of non-orientable cobordisms. So just to let's just first define that. So the non-orientable genus, so the genus of a non-orientable cobordism, or let's just write the non-orientable genus of a cobordism sigma is going to be defined to be, we'll write it as gamma sigma. It's 2 minus the Euler characteristic of sigma minus n, where n is the number of boundary components. So in particular, if it's a cobordism between knots, oops. Then cobordism, then the non-orientable genus is going to be minus the Euler characteristic. Okay, so there are some bounds on this. So there have been some recent papers that have given the bounds for this, for gamma sigma, for various cobordisms. So some of these have been shown by Batson in a paper, and there's some other ones by Osva, and Stipschitz and Szabo, and there's something by Gola and Marengen, and by Haofei Fan. And these are mostly using an unorientable version of the knot floor homology, which we're also going to be talking about a little bit more today. I guess, except Batson's result, which used some more topological arguments. But I guess the question we want to study, so the question we're going to study is, if there is a cobordism, a non-orientable cobordism of a certain genus, how complicated does it have to be? So in particular, we mean in terms of, so if you sort of write this cobordism, let's say from K1 to K2, then you might, you might consider like the number of minima like this, the number of maxima, and then maybe you have some saddles. So how complicated in terms of local minima, maxima, and saddles. Okay, so just to like review sort of a little bit about this question. So there is a recent paper by Juhans, Miller, and Zemke that studied this question for a recent paper that studied this question for orientable cobordisms. And they showed some inequalities relating the genus the number of maxima, and the torsion order in knot floor homology. And our result is going to be the non-orientable analog of theirs. Okay, so we're going to be, in particular, we're going to be using a version of knot floor homology and a version of singular instanton floor homology that is for which, you know, non-orientable cobordisms also induce maps. So the version of knot floor homology we're going to be using, which we'll call HFK prime. This is Osvath, Stipp, Schitz, and Szabo's unoriented knot floor homology. And it's a module over Fu, the polynomial ring, where F is a field of two elements. And then what we're in particular going to be using is the torsion order, which is going to be defined as the minimum n such that u to the n kills the torsion. Okay, and then the version of instanton floor homology, The version of instanton floor homology we're going to be using is it's a singular instanton homology. Instanton homology with local coefficients. With local coefficients. This was defined in a recent paper by Kronheimer and Mrówka. And it's going to be a module over a ring R, which is the ring of Laurent polynomials in 3 variables over the same field. So this F is F2. Okay. And then for this, in this ring, there's these 2 specific elements that we're going to be talking about, which is they're just defined explicitly in terms of these, in terms of the variables. So Q2. Okay, and it turns out that the torsion part of I sharp K gamma is going to be killed by powers of p. So we're going to define the torsion order as the minimum number of powers of p that you need to kill the torsion. Okay, so the theorem, the main theorem I'm going to be talking about, which is joint work with Marco Marengen, is for knots K1 and K2 in S3, if there is a non-orientable cobordism sigma in I times S3 from K1 to K2 with M local maxima, then the torsion order of K1 is less than or equal to the maximum of the torsion order of K2 and M plus this genus of the cobordism. This is the instanton version of the theorem. And then there's also the knot floor version, which is pretty much the same. Except that there's this extra term plus this extra plus one. Okay, so I guess like to explain a little bit like why there's this plus one here, let me just point out that, so I stated this theorem for non-orientable cobordisms, but it turns out that actually the same is true for orientable sigma. And also, actually, you don't need, and in that case, you don't need this plus one. This plus one over here. And actually, like just, you know, just to be clear here, so this, our result is the non-orientable version of Juhas, Miller, and Zemke's result. And for their result, it's actually stated exactly the same way. And if you're looking at the orientable case, like the proof is also the same. So you can just apply their proof directly. The reason that things are a little bit different in the non-orientable case, which is also the reason we need this plus one, is that like in order to define these maps in like for HFK prime, in order to define these maps, you need the maps induced by cobordisms. You need this extra decoration. And this decoration is basically going to look like some like arcs that go sort of from one end to the other. And for the non-orientable case, or sorry, for the orientable case, in the HFK case, you can actually just take a pair of like parallel arcs that just sort of follow like one point along the cobordism. But in the non-orientable case, if you have some kind of like non-orientable tube, I mean, that doesn't really make sense. Tubes are always orientable, but some tube whose orientation is not consistent with like the orientation of the rest of the cobordism, then it turns out that this actually, like, if this is non-orientable, then a cobordism like this with decorations that look like this doesn't actually define a map. So it doesn't actually induce a map in this unoriented version of HFK. So in order to make it induce a map, you basically have to like kind of like thread this this decoration through the like non-orientable cobordism. So, and then like after dealing with that, somehow in order to like make this extra decoration go away, we end up needing to add another +1, like add another tube to the argument. And then for the instanton case, the way this argument is going to work is basically like if you have some non-orientable cobordism, like in order to define a map, you need this decoration. So usually when you define a map for a cobordism sigma, there's this decoration where omega is a surface in S3 times I, whose boundary is on the cobordism. And then in this case, this map, like if you just took in the orientable case, you can like prove this theorem by just taking omega to be empty. And then you run the same argument that Juhasz, Miller, and Zemke runs, and it works. But for non-orientable cases, like, well, you could still take omega to be empty, but if you did that, and like there's still a map induced in instanton floor homology, but usually this map is actually going to vanish in like a lot of the cases that we care about, and not actually going to give you any information. So so we need to, like, in this non-orientable case, we need to pick omega like more carefully. Okay, so yeah. Okay, so before I talk about how to show this, I'm going to talk about a few corollaries of this theorem. So one of the corollaries is, so the theorem here, it gives a bound for the number of maxima. So in particular, like, you can just immediately make a conclusion about ribbon cobordisms. So corollary for a ribbon cobordism sigma, which means this is a cobordism with no local maxima. From K1 to K2, we have that the torsion order of K1 is less than or equal to the torsion order of K2 plus the genus, and the same is true in knot floor plus gamma sigma plus 1. Oh, sorry, let me just say one more thing about the +1. So actually, we don't actually have examples for which the +1 is necessary. So it's possible that you actually don't need the +1. We only used it, like had it for because of some technical reasons to make the actual like technical part of the proof go through. So, but somehow all of these corollaries are going to carry a +1 from this. Also, another thing to point out is that our theorem somehow for the instanton version is sharper, right, in the sense that it doesn't have this +1, but also it's like somehow a lot harder to compute these torsion orders. So like in that sense, like having this result for HFK is somehow better. Okay, so this result just follows immediately from the theorem, because like basically you plug in capital M equals 0 because there are no local maxima, and you get this. Okay, so to derive some more other results from our theorem, I'm going to let's give a definition. So Juhasz, Miller, and Zemke in their paper defined a refined cobordism distance and showed some things about that. And we're basically going to do that, but not orientable anymore. So we're going to define the, let me just say, there's all, okay, sorry, let me just, the refined cobordism distance, the refined unorientable cobordism distance, distance. Okay, so how we're going to define it is for, what the refined cobordism distance in their paper does is basically, the cobordism distance basically asks, how big the genus between, like, if you have a cobordism between two knots, how big the genus has to be. The refined cobordism distance is basically like a little bit, it's going to be larger than the cobordism distance. It's basically going to ask how big the genus is, plus like how many local maxima and minima you need to have. So the refined cobordism, unorientable cobordism distance, the way that we define it is going to be, we're going to like say that the sort of norm of a cobordism is going to be defined as the sort of number of maxima or minima you need to have minus the Euler characteristic. And then we'll define this cobordism distance as the minimum, is the minimum of this norm of sigma for sigma varying over non-orientable cobordisms and also over concordances, which are orientable. So it's sort of varying over the set of all concordances and all non-orientable cobordisms. Okay, and then there's also the standard unorientable cobordism distance, which is given by the minimum of the genus, where sigma again varies over this. It varies over these two sets. Okay, so I guess it's not hard to see that the standard cobordism distance is a distance on the concordance group, and the refined version is a distance on the set of knots up to isotopy. Okay, and our result is that the refined cobordism distance has a lower bound in terms of the difference between torsion orders. So ord ik1 minus ord ik2 is less than or equal to the refined cobordism distance. And for the knot floor version, this is also not very hard to see from our theorem, because just to do the instanton version, because what you can do is just say, well, this order is less than or equal to the maximum of ord I, K2, and M plus gamma of sigma, and then this is just going to be less than or equal to the sum of the torsion order of K2 and M, after which you just you can move the K2 to the other side, and you get this. And so this gives you like the bound on order of K1 minus order of K2. And then if you want the bound on order of K2 minus order of K1, you can just consider the cobordism. Instead of going from K1 to K2, you reverse it. So it goes from K2 to K1, and that sort of switches maxima and minima. So we get this is less than or equal to the number of local minima plus this. And then combining these two, you get this inequality. Okay, so what you can use this to show is that the order of or well, maybe not exactly use this, but that the refined cobordism distance between K1 and K2, like, sorry, the difference between the refined cobordism distance and the cobordism distance, the standard cobordism distance, in the unoriented case, so this unoriented versions, can be arbitrarily large. So to show this, basically, what we did was we showed, like, sorry, to show this, we had some computations of this ord u k. And in particular, we showed that for torus knots, Tn+1, the torsion order is the floor of n over 2. And also I guess these other results just sort of follow formally from the definitions and the like Kuhneth formula for HFK, but the order of the connected sum of two knots is the maximum of the torsion orders of each. And K2. And the torsion order of the mirror of a knot is the same as the torsion order of the knot. And so from this, you can from these three, we can sort of compute the torsion order of the connected sum of, okay. So we can compute the torsion order of knots that are like connected sums of things like this, of things like this, and in particular, like, we find that for a knot K gamma M, which is given by this, by the connected sum its torsion order is R-1, but then so then in this case you can show that like the refined cobordism distance from K gamma M to the unknot is actually just equal to R-1. It's this torsion order sort of, sorry. Okay, so sorry, this is not actually what I wanted to do. Let me write it this way. Okay, so what we can actually show is that a cobordism, not a cobordism, a surface sigma with boundary K gamma M has actually at least M minima. And sort of the way to show this is if you have this K gamma M and you have a surface, then you can consider it as a map like from the cobordism from K gamma M to the unknot with like if you had M minima, then this is going to have M-1 maxima. And then you apply the theorem, and then we get that like that the, yeah, okay, sorry. So applying the theorem, you basically can conclude that this that the surface has at least a minima. And so in particular, you get that this refined cobordism distance has to be like arbitrary, can be arbitrarily large. The refined cobordism distance is at least n. Okay. Are there any questions? Okay, so I guess I'm just going to conclude by telling you basically how we showed this theorem, which is, okay, so to show the theorem, so we're using a very similar argument to what Juhas, Miller, and Zemke did. So, so if you have a cobordism sigma from K1 to K2, and you also know that it's non-orientable, then what we're going to do is we can decompose it as first you take K1, and then you can decompose it into like some pieces where first you do the births, then you do these like birth canceling sort of these fusion saddles. So first you do the births and you get a link, which we'll call L1. Then we do some fusion saddles, so you get a knot K1. And then we have a bunch of bands. And like, I guess, you know, for their argument, you could just like sort of put all the bands together. But actually, because our cobordism is not orientable, we're going to try to isolate like one non-orientable band. I mean, like if I just sort of talk about all the bands, you know, you could have orientable and non-orientable ones. But it turns out that actually you can arrange your cobordism such that there's only one non-orientable band. You can do this by basically like moving the bands along the knot and sort of passing them. When you pass one band through another, you basically like you can sort of change it from like orientable to non-orientable to orientable. So what we're going to do is say that first we're going to do like, so we have K1, and then we're going to do a bunch of, we're going to isolate one non-orientable band with respect to, sorry, this is K1 prime, with respect to K1 prime, and we're going to do that one last. So we do all the orientable bands with respect to K1 prime first, and we get L prime. So here this is orientable with respect to K1 prime. And then we're going to do our last band, the one which is non-orientable with respect to K1 non-orientable. With respect to K1 prime. And then we have our deaths and like our saddles that break up the cobordism and deaths. So M bands and M deaths to get K2 at the end. Okay, so the argument that Juhas, Miller, and Zemke did was you basically take this whole thing and you glue it to its mirror. So you do something like this. And then, like, after you've glued it, what we do is we add tubes. You add tubes to like these deaths. And then you get this other cobordism that involves like adding these tubes. And then you want to compare that to like basically the identity. So like after adding these tubes, you can just sort of like add, you can sort of kill these, like, this is, after you add this tube, this thing here, there comes to be a tube like in the middle here, and you can basically cap off those tubes. And so you're just repeatedly using this result where if you have a tube, it's the same as like, you can compare it to like what happens if you cap off this tube. So, and what happens is basically that you pick up a factor of u or p or whichever the variable is. Okay, so the problem in the non-orientable case is that if your tube that you add is like not actually orientable with respect to the rest of the cobordism, then you don't necessarily have like this, you don't actually have the same like this same relation with capping off the ends. So I guess, let me, like, I'm being a little bit vague. So like, to be more concrete, I'm just gonna restrict to one version. Let's just talk about the instanton version. So in the instanton version, if I wanted to do the orientable case, there's a formula that says that the map induced by a tube is the same as this, where you cap off the tube with a dot on one end, and then capped it off with a dot on the other end, plus p times doing it with no dots. And then, but it like this sort of argument, basically like what these dots, they come with orientations that are like compatible with the orientations of the caps. And if I had a tube which was not orientable, like basically instead of having these like things cancel and everything sort of being nice, you end up with a mess. But it turns out that when a way you can sort of circumvent this is like, if I have like, is basically you want to like compute what happens if you take a flip. So you take a cobordism from, let's say, the unknot to the unknot that just sort of flips this, like, so you take this circle and you sort of flip it around and like go to the other, like, so it's a, take the cobordism that sort of does a flip in the middle here. So if I take this cobordism, the instanton floor homology of this is, I mean, this, I guess there's like a formula for this, because the instanton floor homology of the unknot is going to be sort of like free module on two generators, and then this flip, there's like this matrix you can write down for what it is. But this is like sort of not really what we're going to be using. What we end up showing is that if you have this flip cobordism, but there's like some omega going along it. So in this case, if omega is two arcs like this that are sort of fixed by the flip. So what this means is like I have, oops. So I have somehow these like this like omega, it's just on these two ends, and then I'm going to flip in a way that doesn't move omega. So you're flipping like this. Then the map that this induces is actually the identity. So I sharp of this map is actually the identity. So then basically what we want to do is we want this, like, we want the non-orientable tube to like have this non-orientable tube that we're going to create by taking our non-orientable band and gluing it to its mirror. It's going to have some arcs like going down the center, and then in this case, this non-orientable tube like can just be replaced with an orientable one, because you can just like remove this, like you can sort of add a flip to it and not have any effect on the map. And so then like you just don't have this like problem anymore. So just to so I'm just going to show you like a picture of this in a specific example. So in this case, I'm considering just a single non-orientable band from the unknot like to the unknot. And so in this case, or I guess it doesn't, okay, this actually doesn't have to be the unknot, but basically like a single unorientable band between two knots. And in this case, what happens is you do this band, right? And then you're gluing it to its mirror. So that's this like this other piece on the right here. And then what we're saying is like in the middle here, there's this tube and like sort of the center circle of the tube is in blue. And so this tube, sort of what it actually is compared to the cobordism is it's a tube whose orientation is not consistent with that of the cobordism. But what we want to do is basically insert a flip in the center here. So we're sort of flipping this blue circle, like you add a little flip in the center there. And then the idea is that what happens, oh, sorry, I forgot to tell you how I chose omega. So in this case, like we're taking omega, so you have a band, right, which is being added to a knot. So we have some band like this, where there's some knot. And so what we do is basically take omega, you sort of can start omega somewhere in the middle and like just make it be half of the knot, just from, because the band sort of splits the knot into two pieces and you just follow the knot on half of it. And then you just go across the band. So you're going across the band like this. And so in this case, if you do this and you take its reverse, then what happens is like we can look at the center, and it turns out that if you add another flip to the center, then what you end up getting is that this entire omega becomes like, basically becomes contractible. Like, so you can just sort of push the two ends in and they'll like collapse. And so then what you end up getting is that the map induced is the same as not having omega, but also like the cobordism becomes orientable when you add this flip. So then you can do the exact same argument as Juhasz Müller-Zemke does, because now you no longer have this non-orientable tube. Okay, so in the HFK case, HFK prime case, you sort of do the same thing, except the problem is that at the end, after you've done this, like after you've sort of gotten rid of the flip, what we had is that we had this like omega that's sort of now going through this tube. But like somehow this omega with like thing with omega going through the tube, you can't actually just like collapse the tube in this case, the way we can in instantons. So the way to get around this is by basically adding another little piece with another tube that omega goes through. And then you can basically collapse the two tubes at the same time. And then, so this, in the HFK case, we add, add another tube, and then we can collapse both tubes at the same time. But that's sort of what this results in the +1 term. Okay, I think that's all I had to say for you, so I guess I'll end here.
Well, are there questions?
Well, I'm not sure if this is a question or comment, but I think Ballinger, he had also some work involving Koanov homology to get some some bound and non-orientable genus. Do you guys know if it can be combined with your techniques to get some result, in the context of Gowanov homology.
Oh, I had not heard about this, so I'm not sure.
Yeah, I think this is very recent, like during last year, I think.
I see. Okay. Thanks for letting us know.
Well, also the question, at the recent AMS meeting, Vincent Longo gave a talk comparing the pinch number to the four-ball genus for torus knots, seeing that they are not the same. And he had numbers of cases worked out, but there was a fairly small torus knot where he couldn't work out precisely what happened. Have you thought, does this say anything about pinch number versus the cross cap or non-orientable genus?
I'm not actually familiar with what the pinch number is. What is it?
The pinch number is essentially the 3D version of the cross cap number.
Oh, I see. Yeah, I'm not really sure about any relation with this.
Did you compute the torsion index for instant on floor homology of Tn n+1, or the torus knots that you mentioned?
We were not able to do this. I think these instanton homologies are somehow, they're pretty hard to compute. So I'm not really sure how one would do something like that.
Do you want to remind me of where the red lines come in the cobordisms in the instanton theory? I've seen a couple talks but haven't.
Oh, yes. So the red lines, I guess the omega is, so if you have the instanton floor homology, you're usually working over a singular bundle. And it's going to be an SO3 bundle that doesn't lift to an SU2 bundle, and the omega is really like the Poincare dual of the W2 class, which sort of measures the non-liftingness of the SO3 bundle to an SU2 bundle.
Okay.
Yeah.
As we're chewing on this, I will suggest that everybody have a happy Halloween and notice the blue moon. I'll also suggest that because it's the once in the blue moon, at least in North America, there's this time change that's going on. And so when we convene next week, remember to check out the time correctly.